Good evening, sir.
Good evening.
Uh,
Audible ആണോ?
yes, audible on.
ഇതില് നമുക്ക് പുറത്തുള്ള ആരെങ്കിലും ഉണ്ടോ മലയാളീസ് അല്ലാത്ത?
ഉണ്ട്. ആ. Starting and
സ്ക്രീൻ ഷെയർ ചെയ്യാം.
good evening all, good evening everyone, and welcome to this third session of our 40-day crash course. Today we'll be having the class on electronics and experimental methods. So the section will be handled by Sharaf Ali sir. Sir, you can start the session.
Okay, is the screen visible?
Yes, sir. Yes, sir.
Okay. Okay, we will start the uh, digital electronics first in the electronics section. And in that digital electronics, the fundamental questions that can come from this section, which is the logic gates. Okay. Audible alle? Is it audible? Okay. So in this logic gates section, we have different types of logic gates. We will not be discussing much theoretical part of this logic gates or any other topics. We'll be covering all the sections in such a way that you can be able to, we'll be able to answer the questions, okay, all the questions or the problems, okay. So we'll be focusing on problem side more in the crash course. While if you are joining for some other long period courses, then we can discuss the theories, okay. So in this section, we will be discussing all the problem side of these sections, different sections, which will be coming in your CSIR next exams. Okay, so we will be starting with these logic gates. As you can see from here, you have different types of logic gates. And the first one is not that much important, which is nothing but the S gate, which is if you are having an input, okay, if you are having an input, so this side you can see, I hope you can see this gate, S gate. So if you have any input at this side, okay, the output is denoted as A here, and the output will be same as the input, okay. So whatever you are giving as input, that will be your output. That is the output of this gate, but this is not that much important for your exam point of view. But when you consider the second gate, which is the NOT gate, this NOT gate, if you are giving any input, you are considering input as A here, put as A, then you will be getting the complement of that input at the output. you can denote that complement of the input either by a dash, or you can also represent this as a bar. Okay, both are okay, or you can also use a star. All this representing the complement of this input a. Okay, so when you are giving an input, the output will be the complement of that input. The complement means in the logic gates we will be using only zeros and one, zeros and one. These are binary digits. These are binary digits. If you have any problem with the visibility in this writings or any other problems, you can just let me know. Okay. So you will be using 0 or 1 in the case of the binary system. In logic gates, we'll be using that binary format. So 0 represents a low voltage, and 1 represents high voltage. So this simply represents low and high voltage and low voltage. So which means if you are using a 5 volt, okay, which can be represented as a 1, which is high, which is simply saying that this is high volt, this is high volt. And if you are using some 2 volt, which you can represent as 0, which means it is a low volt. So this is the representation that we use in digital electronics, which means that all the high voltage signal, we will be representing as 1, and all the low voltage signal we will be representing as 0. So we will be using this 0 and 1 in digital circuits, which is nothing but the binary numbers. Now, if you are considering any of these digital or the binary numbers as your input, which means you are giving a high input or you are giving a low input at the logic gate node. Okay, if you are giving that input at the node, then the complement of that input will be the output. For example, if you are considering this truth table for this NOT gate, then you can see this is your input A, and you are giving 0. Okay, you have given 0 as input, then the output will be 1, which is just a complement of the input 0. And if you are giving 1 as input, then the output will be the complement of that, it is 1. Sorry, it is 0. Okay, so if you have given 0, then complement of that is 1, which means if you have given low input to the NOT gate, it will give you high output. If you have given high input at the NOT gate, then it will give you low output. Okay, that is the meaning. Or if you are giving low voltage at the input, it will give you high voltage at the output. Or if you are giving high voltage at the input, it will be giving you a low voltage at the output. So this is the action of NOT gate. It is just complementing the input. So if you have given 0, then it will give you 1. If you have given 1, it will give you 0. So that is the action of NOT gate in digital circuit. Now we will be moving on. This third one is AND gate. AND gate is very simple. First of all, you need at least 2 inputs for AND gates. You can see here for AND gate, this is the symbol, representation or symbol of the AND gate. You have 2 inputs. In this case, you are using 2 inputs as A and B, variables A and B. Okay. So at least 2 inputs you need for AND gate. But in the case of NOT gate, you can see that the for NOT gate you need only 1 input. You can see here you have only 1 input. Okay. So for AND gate you have 2 inputs A and B, and the output will be the product of the inputs. Okay, then you can consider it as a product, but we call this as A and B, but the mathematical expressions that is given by the output will be equal to a dot product. Okay, so we can just consider it as a product operation. So if you are giving A and B as the inputs, then it will give you A dot B or A into B as the output. Okay, when you read that, it is A and B. Okay, then input, you can see here the truth table inputs are A and B. When you have given 0 and 0 as your input, then the output will be 0 because the product of 0 and 0 is 0. And when you give 1 and 0, the product will be 1 into 0, that is also 0. When you give 0 and 1, the product is 0 into 1, that is 0. When you give 1 and 1, the product will be 1 into 1, that is 1. Now, the important conclusion that you can get from this truth table is, in the case of AND gate, the output is 1 only when the two inputs are high. You can see here, when the two inputs are high, at that time only the output will be maximum, or the output will be high. In all other cases, the output will be minimum. Okay, so or in the when the inputs, both the inputs are high, at that time only the output will become high for AND gate. Similarly, if you consider OR gate, you can see here OR gate. This is the symbol for OR gate. I can just draw here for your. You can see this is the AND gate symbol. This is the AND gate symbol. Okay, so you have to give two inputs, A and B, and you can get the output at this point, Y, which is equal to A dot. Y is equal to A dot B. Now, if you consider OR gate, this is a little bit something like this for OR gate. Then you have two inputs again, like AND gate, A, B. Then the output will be Y equal to A or B, or the operation you can consider it as A plus B. This operation you can consider as A plus B, but it can be read, normally we read that as A or B. Okay, so A or B means it is just addition of variable A and B. Okay, so when you consider the truth table of OR gate, you can see these two are the input A and B, and when both inputs are 0, when both inputs are 0, this is 0, this is 0, then the output will be 0 because 0 plus 0 is 0. When the input A is 1 and B is 0, then you can consider this as 1 because 1 plus 0 is 1. Then third one is 0 and 1. Then 0 plus 1 is 1. And the last one is 1 plus 1. 1 plus 1 also will be 1. Why 1 plus 1 is 1? Because in binary number system, you have the maximum value which is 1. More than that is not possible. Whatever the value which is more than 1, you can treat it as 1. Okay, so the maximum value will be 1. So 1 plus 1 will be always 1. Maximum will be 1. So because of this, you can conclude from this truth table, the output of OR gate will be 0 when both the variable or both the inputs are 0. Previously, we told that when in the case of AND gate, when both the inputs are 1, the output will be 1. For the case of OR gate, when both the inputs are 0, the output will be 0. Okay, or simply you can just write this A and B and just add these variables, then you will get the output. Similarly, for AND gate, you just take the product of them, then you will get the output. Okay. Then the fifth one, logic gates, which is XOR gate. XOR gate. This is nothing but exclusive OR gate. Okay, XOR means exclusive OR gate, and in the case of exclusive OR gate, the output will be A bar B plus AB bar. Output will be A bar B plus AB bar. I will just draw that diagram here, symbol. So this is your XOR gate. So in this case also, you have two inputs, at least two inputs you need. And you can see from here, this is A, B are the inputs. And your output Y will be equal to A bar B. A bar means A complement B. Then plus AB bar. AB bar. This is the output. A bar B plus AB bar. This is the output of XOR gate. exclusive OR gate. Now you can just substitute the value for A and B in this expression. You have inputs A and B here in the truth table. Then 0, 0. If you consider A equal to 0, B equal to 0, substitute that in this expression. Okay. A equal to 0, B equal to 0 in this expression. So first term A bar, okay, I will just do that. Let's say A equal to 0, B equal to 0. Then what will be the Y value? Y equal to A equal to 0. But you are taking A bar here. So A bar will be 1. Okay. A equal to 0 means A bar will be equal to 1 because it is just a complement of that value. Complement of 0 is 1. Then you will get 1 into, okay. Then you have B. This is A bar B means A bar dot B. Okay. A bar dot B. So A bar B, which is 1 dot B. B is 0. B is 0. So this is 0 plus the second one is A dot B bar. A is 0 dot B bar is B is 0. So B bar will be 1. B bar will be 1. So in that case, you will get 1 into 0, that is 0 plus 0 into 1, that is also 0. Then you will get 0. So your output Y will be 0. Okay. So in this way, you can substitute other inputs. For example, when you can, in case one more case we can discuss for this one. So you get, for example, second case. We'll just erase this thing. I will just erase. Okay. So for the second case, you have 1 and 0. For A equal to 1 and B equal to 0, in this case, what will happen? A equal to 1 means A bar is equal to 0. When A is 1, A bar is 0. And B equal to 0, B bar is equal to 1. So in this case, what will happen? Y will become, that is A bar B. A bar B means A is 1 now. So A bar is 0. So 0 dot B. B is also 0. Okay. Plus then A B bar. A is 1. A is 1. And B is 0. Then B bar is 1. B bar is 1. So this is 1 dot 1. So finally you'll get 0 dot 0 is 0 plus 1 dot 1 is 1. Then you will get 1. So this is how this output will become. And the third case 0 and 1, then also you will get 1. And in the last case you will get 1 and 1 for inputs. For A and B we have 1 and 1. Then in that case you will get 0 as the output. You just substitute that in this expression, then you can verify the truth table. Okay. So what you can conclude from here in the truth table of XOR gate, exclusive OR gate, if both the variables are same, if both the variables are same, which means inputs, okay, variables means inputs. If both the inputs are same, then the output will be 0. That is the conclusion. For the case of XOR gate, if both the inputs are same, then the output will be 0. If the inputs are different, then the output will be 1. If you know this thing, then you don't have to do all these calculation every time when you consider these circuits. Okay. So just to understand that in the case of XOR gate, if both the inputs are same, then the output will be definitely 0. Okay. So keep that in mind when you do the problems. If you know that, then you don't have to do all the substitution and so on. Okay. The next one is NAND gate. NAND gate, you can see this is very simple. NAND gate. NAND gate is just opposite or the complement of the AND gate. Complement of the AND gate. This is just NAND gate. You can see here. This is an AND gate. You just draw an AND gate with two inputs. Okay. So AND gate with a dot or a bubble. This is called a NAND gate. Okay. This is equivalent to a AND gate. This is your AND gate. This is followed by a NOT gate. This is followed by a NOT gate. Okay. So whatever the output of AND gate, which will be complemented by this NOT gate, yeah, that is the NAND gate operation. So it is just a complement of the AND operation. And that you can also see from this truth table. You can see that from this truth table. I hope you can see all these values. So this when A equal to 0, B equal to 0, the output will be 1. Because when you consider AND gate, 0 into 0 is 0, then taking that complement of that value will be 1. Okay. Then you consider 1 into 0. Just consider AND gate operation, then take complement. 1 into 0, 1, the second case, 1 and 0 are the inputs. So 1 into 0 is 0. 1 into 0 is 0. And that is AND operation. Take complement of that. Then you will get 1. Then 0 into 1, 0. Take complement of that. It will be 1. 1 into 1, that is 1. Take complement of that. It will be 0. So when you consider NAND gate, you just consider AND operation, then take complement of that. You will get the output. In the same way, when you consider NOR gate, it is the same scenario. You have an OR gate. This is your OR gate with a bubble. Okay, this is equivalent to a OR gate, followed by a NOT gate, followed by a NOT gate. So whatever you are getting as the output of the OR gate, which will be complemented. Okay, that is the expression you can see from here. The output expression is A plus B complement. A plus B complement. So when you take A plus B, first you have to take A plus B, just like OR gate for the case of OR gate, then take the complement. So for example, in the truth table, you can see when the input A and B are 0, when the input A and B are 0, the output, when you consider OR operation, this is 0 plus 0, that will give you 0. Then you have to take the complement for NOR gate. Okay. So 0 plus 0 is 0. When you take complement of that, you will get 1. That is the output of NOR gate. And 1 plus 0. 1 plus 0 is 1. Take complement, then you will get 0. 0 plus 1 is 1. Take complement, you will get 0. 1 plus 1 is 1. Take complement, then you will get 0. So just a complement of the OR gate, that is the NOR gate. And similarly, you can see XNOR gate. XNOR gate, only you can see again a bubble after that XOR gate. XOR gate, you have the XOR gate up to this, and then you take the complement. So complement of XOR gate will give you XNOR gate, exclusive NOR gate, exclusive NOR gate. So in this case, you have two variables as you can see from here. And if you consider XOR operation, 0 and 0, because both inputs are same. When both inputs are same for the XOR gate, the output has to be 0. When both are same, the output has to be 0. So in this case, you have to take complement because it is XNOR gate. You have to take complement of XOR gate, then you will get 1. And 1, 0. In the case of 1, 0, the inputs are different, then you have to get 1 for XOR gate. If you are using XOR gate, then you should get output as 1. Then for XNOR gate, you have to take the complement, then you will get 0. And third one, 0 and 1, inputs are different. So for XOR gate, the output has to be 1. But in the case of XNOR gate, you have to take complement of that, then you will get 0. Then 1 and 1, both inputs are same. So for XOR gate, you should get 0. So for XNOR gate, you should get 1. Complement of 0, that is 1. So these are the important gates, all the logic gates that we have to consider when you look into the problems, different logical circuit problems. Okay. So if you have any doubts in this section, any steps or any diagram or any truth table, you can ask now. Within 1 minute, you can ask. Okay, then if you don't have any doubt, then we'll move on. So these are the logic gates. Now we'll consider some problems with these logic gates. Okay. So the first problem you can see here. This is the first problem. First, you try to solve this problem. Just try this problem by yourself. Okay, just draw this diagram and just try to do this within one or 2 minutes. Or I will just do this first one. You can just you can also do by yourself. So in this question, this is a previous year question also. So the logic circuit shown in the figure below implements the Boolean expression. So they are asking what is the output expression for this circuit. Okay, the logic circuit shown in the figure below implements the Boolean expression. You have different options: a dot b all bar, a bar dot b bar, a dot b, then a plus b. And remember that all the questions which comes from this logic circuit part, especially from this the logic gates part, that will be very easy if you know how the logic gates works. Okay. So first you have to understand which are the logic gates used in here. So you can see here the two logic gates are
Option A, sir.
option A. Okay. Anybody else? Anyone else got the answer? Okay, I will just explain that anyway. So you have two XOR gate. You can see one XOR gate here, one XOR gate here, and an OR gate. So this is the first step. And in all the logic circuit, first what we have to do is you have to go with the circuit. Okay, you have to go with this circuit. So when you consider in this problem, you can see this arm or this line is always high. Then high means what is high? High means it is one. Just use this thickness. High means it is logic is high, which means it is binary value is 1. Okay, so this line is always 1. Then you have input A and input B, input A and input B. So this arm is having input A, this arm or this line is having input B. Okay, input B, and this line is having high, this line is also high, which is coming from this line. Okay, then as you know, this is the XOR gate, and for the output of this first XOR gate, you consider this one. So the first XOR gate, the output Y is equal to, as you know, the output will be first, you can consider A bar dot 1 plus A dot 1 bar, A dot 1 bar. Okay, so one is one, the inputs are A and 1. Inputs are A and 1. So I just wrote in the same way, okay, as the expression. So you can see this A bar dot 1 is nothing but A bar. A bar into 1 is A bar plus A into 1 bar. 1 bar is 0. Okay, complement of 1 is 0. Then this will be A into 0. Okay, A into 0 is 0. So this simply gives you A bar. This simply gives you A bar. Same scenario, you can see the other XOR gate, because you have one input which is B, the other input is 1. So in the second case, you will be getting, so this is the output of the first XOR gate, and the second XOR gate you will be getting, instead of A bar you will be getting B bar. So here you are getting A bar, here you are getting B bar. So this is how you go with the circuit. You just write down in the circuit, then you can easily find out what is the output. So this side you have A bar, this output of this XOR gate is A bar, output of this XOR gate is B bar. One more thing you can see is that if the second input of XOR gate, okay, second input of XOR gate is high, then the output of that XOR gate will be complement of the first input or the other input. You can also consider it as, if one of the input is high, okay, then the output of the XOR gate will be the complement of the other input. Okay, that is the result. Similarly, you can consider 0. If one of the input is 0, if the one of the input is 0, then the output of the XOR gate will be the other input. This is the conclusion that you can get from here. So if one of the input is high, then you will get complement of the other input. Then you can directly, if you know that, then you can directly. So these kind of tricks you can, if you use in examination, then you can do all the problems in a much more faster way. So this is the result of XOR gate. After XOR gate, you will be having A bar and B bar. Then this A bar and B bar will be going to the output. A bar and B bar will be going to the output. So this A bar will be reaching here, then B bar will be reaching here. And what is this gate? This gate is OR gate. This is OR gate. Then what is the expression of OR gate? OR gate is nothing but plus. So you'll get output as A plus, sorry, A bar plus B bar. You'll get output as A bar plus B bar. Now you can see any of the option with the A bar plus B bar. You cannot see any of the option with A bar plus B bar. But there is one theorem. I will just discuss that shortly, which is the De Morgan's theorem. De Morgan's theorem. It says that if you take the complement of A plus B whole bar, then you will get A bar dot B bar, which means complement of the variables and complement of the operator. Okay, plus will become dot, and A will and B will become A bar and B bar. Similarly, A dot B whole bar, if you take, then that will become A bar plus B bar. Dot will become plus A, B, this two will become A bar and B bar. We will discuss this theorem shortly. Then this is the result. This is the De Morgan's theorem. So once you solve the problem, then if you know the De Morgan's theorem, then you will get the option A as your correct answer. Y will be A dot B all bar. A dot B all bar will be equal to A bar plus B bar. A bar plus. Okay. Now consider the second problem. This one was we also need this De Morgan's theorem here. So we'll discuss that different theorems that we'll be using in Boolean algebra. Then you will be will understand that more clearly. But this one is direct. This one you can easily do because it is just you have to substitute the numbers. You don't need any theorems or expressions here. You just substitute the numbers and find out the answer. This is a question. Consider the digital circuit shown below in which the input C is always high. Okay, input C is always high. This C is always high. That is given. And the truth table for the circuit can be written as, so you just have to fill this final column Z value or the output of the circuit. The entities or the entries in the Z column vertically are. That is the question. So which are the values which will come in this column? This is also a previous year question. So you just do it in 1 minute. 1 minute. Just substitute a. You have this variables a and b here. Okay, just substitute a, b value here. C is always high, so don't worry about that value. This is always 1. Okay, just substitute the other values and find out what is the z value. Okay, just try to do it.
Option D, sir.
Okay, uh, somebody said option D. Let's wait for some time. That other thing.
Option D, sir.
Okay, let's do it then. Okay, so this C is always high. Meanwhile, the others also can try. Okay. If you are stuck with any steps, you can just follow me. Okay, so C is always high. C is always high. Only you have to consider A and B. Okay. So this is you can do that all these steps A and B for all these values you can do, or you can just consider these options also, option A, B, C, D. Then find out which one is different. If there is any value which is different, which digit is, so you can see from here the last digit is here. The last digit is 1. This is 1. This is 0. This is 0. When you consider first one, this is 1, this is 0, this is 1, this is 1. Okay. So either you can start with first one, or you can start with the last one, or you can start with the middle one. If there are three of them which are coinciding. Okay. So that is an approach. Just I'm just saying that this is an easy. So just to consider 0, 0. If you consider 0, 0, A and B are 0, 0, then just put 0, 0 here, 0, 0. Then 0, 0 will be coming here. This is AND gate. You can see this is AND gate. So this is AND gate, this is just a product. Okay. Whatever the input, it will take the product of the input as the output. So 0 into 0, that will give you 0 at the output of the AND gate. And this 0 is coming through this line and reaches at the one of the input to the OR gate. Okay, one of the input to the OR gate. At the same time, this B is connected to this XOR gate and C is 1. As we discussed earlier, if any one of the input to the XOR gate is high, then the output of the XOR gate will be the complement of the other input. Okay, so whatever you are getting here, it will be B bar. The other output is B, so B bar. So when you are having B equal to 0, you will be getting this value as 1. B bar is equal to 1. Or you can just substitute 1 and 0 in the case of for the case of XOR that expression. Then also you can get 1 as the output. Then when this is 1, this is 0, then XOR OR gate output will be 0. This is 0, and this one is coming here. So 1, 0 plus 1 is 1. So the first output, this one will be okay. So in this case, you are eliminating this B. In this case, you are eliminating that B, because all others are having the first digit as 1. So now you have you consider this 1, you have 1 0 1 0, then you have 1, sorry, this is already eliminated. This is 1 1 1, then 0 1 1, 0 1. Okay, so in this case last one is 0, this is 1, this is 1. Now let us try to do with the last one. You can try, or you can just go in the same way. Both are possible. So for this we can save some time, or I will just explain all the cases, because it's better to explain all the cases. Okay, second one is 0 1. So A is 0, B is 1. So when A equal to 0, B equal to 1, AND gate will be 0 into 1, that is 0 here. Okay, that 0 will come here. Then now B is 1 here. The complement of that will be output here. So B bar is 0. So 0 0 will come to the OR gate. Then you will get output as 0. So the second one will be 0. Then third one is you have A equal to 1 and B equal to 0. A equal to 1, B equal to 0. So in that case, 1 into 0, 0 will come here again, 0. And this one, B bar will become 0 bar. 0 bar is 1. And 1 and 0 will come here. Again, you will get, I think I have made a mistake. This is 1. Okay, this is okay. This is 1 plus 0. Then this will come as 1. 1 plus 0 is 1. So you'll get 1 here again. And the last case is 1 and 1. Just B is going to become 1. When it is 1 and 1, the AND operation will be 1 dot to 1, or 1 in 1 and 1. So 1 into 1 is 1. So that 1 will come here. And complement of 1 is 0. That is 0. This is 0. And OR gate 1 plus 0, the output will become again 1. So this is the output. And the option D is correct. So 1 0 1 1 is the correct answer. So these kind of problems are very easy. Only thing that we have to do is we should know how the gates work, how the what will be the output of the gates when you have the inputs are given. If you know that, just write everything in the circuit itself. Don't do any calculations in your mind, because in that case sometimes the calculations may become wrong. So better to write like this, all the digits or the expressions in that circuit itself, then it is easy to solve. Then there is a possibility, there is no possibility to get wrong. Okay, so that is the method. So these kind of problems are very easy. I hope you understood these two problems, and we will do the other problems also. Okay, so if you have any doubt in these two problems or any previous sections, you can just ask me any of the steps. If you missed or you didn't understood, you can ask quickly.
So in the previous sum, the answer is A or C, sir.
Which one?
Previous sum, previous
Previous
problem.
one. Okay, previous problem.
Answer is A or C.
Answer is A.
Oh, because A bar plus B bar, when you take A
Yeah,
bar plus B bar, when you take the whole bar, it will come A dot B, no?
no. In case of De Morgan's theorem, I will just explain that De Morgan's theorem. Should have done that first. Anyway, so this is in the first problem. You have this De Morgan's theorem. That is, if you are taking A plus B all bar, if you are taking A plus B all bar, then that is A bar dot B bar. A bar dot B bar. As I have written here, you can see here.
I
A bar
understood
dot.
about A bar plus B bar.
Okay.
When you take a bar for a bar plus b bar,
Okay.
it will come a dot b, na sir? Answer C or A?
Now we have to get this answer, right? A
Yeah.
bar plus B bar. A bar plus.
Yes, sir. I understood that. A bar plus b bar.
Okay. Then that will be coming when you take the complement of A dot B whole bar. Then this will become, first you take the complement of A, that is A bar. Then you take complement of dot, then that is plus. Then you take the complement of the other variable B. So this is B bar.
Okay.
So that is equal to your output.
Okay, sir. Thank
So
you.
sometimes they will not give the right answer readily. There will be some kind of this kind of modification. So in that case, you should know the De Morgan's theorem also. So you should know the logic gates operation as well as De Morgan's. Then only you can solve that.
Okay, sir. Thank you.
So anyone else have a doubt? If you have any doubt, you can ask.
Excuse me, sir.
Yeah.
Sir, here for option A, it is A dot B the whole bar, and option B, it is A bar dot B bar.
Yes,
So A dot B the whole bar is the correct answer, right?
yes.
Okay, sir.
Then only it will come plus.
Yes, sir. Yeah, A is correct. Okay, sir. Thank you.
Thank you, sir.
Okay. Now let's move to the next part, which is the theorems or laws in this, which will be used in binomial uh, simplification of the binomial expressions or Boolean expression. You can say this is Boolean expression. So these are some simple laws which will be used to simplify these kind of expressions in this solving different kind of logical problems. We'll be using this kind of laws. So these laws are very simple. Some of them are very familiar to you. Some of them are tricky. That might be asked in the questions in the exams also. Okay. So we'll discuss quickly one by one. I hope you can see this screen and it is visible. So this is first one. You can see identity law. You don't have to remember these names. That is not that much important for the exam point of view. You just need to know what is the output of each of these laws. So first one is identity law. In the identity law, you see here law of addition and law of multiplication, which means if you are using OR gate, what will be the output? If you are using AND gate, what will be the output? Okay. So if you consider x plus 0, x plus 0, this first one, I hope you can see that. Just zoom it. Okay, x plus 0 is nothing but x. This is very simple logic. If you add anything with 0, you will get the same thing. That is the, so that is the identity law. You will get the same thing. Okay, x plus 0 is x. Okay. Similarly, x dot 1, that is also x. X dot 1 is x. X plus 0 is x. X dot 1 is x. Now x plus x bar. This is complement law. So I will not be mentioning these laws, the theorem or laws, but just remember these expressions. Okay. So x plus x bar or x plus x dash, which means if you are adding a variable with its complement, that is this expression x plus x bar. When you add a variable with its complement, you will get the answer as 1. That is x plus x bar is equal to 1. So you can just substitute some value for that. You can easily get that. If you are substituting x equal to 0, then your the expression will be 0 plus 1 because x bar will become 1. Then 0 plus 1 is 1. If you are substituting x equal to 1, then it will become 1 plus 0. Then that is also 1. So if you add a variable with its complement, then that will be equal to 1. At the same time, if you multiply a complement, a variable with its complement, then that will be 0. Suppose if you put x equal to 0 here, then this is 0 into 1, that is 0. If you put x equal to 1 here, then 1 into 0, that is also 0. So if you multiply a variable with its complement, then you will get 0. If you add a variable with its complement, you will get 1. Okay? That is the complement law. And the third one is idempotent law. That is x plus x is x. X plus x is x, which means if you add a variable with the same variable, then you will get the same variable. Like a plus a is a, okay, or b plus b is b, or 0 plus 0 is 0. Similarly, 1 plus 1 is 1. So if you add a variable with the same variable, you will get the same variable. Or if you add a value with the same value, then you will get the same value. Similarly, if you multiply a variable with the same variable, you will get the same variable. Like a dot a will not becomes a square, but a dot a is a. Similarly, b dot b is b. 0 dot 0 is 0, 1 dot 1 is 1. Okay, that is idempotent. You will get same x. Whatever variable it is the output will be the same. And now if you consider x plus 1, this is a dominant law. Dominant law means 1 will be always dominant here. X plus 1, you don't have to bother about x here because always the answer will be 1. Whatever variable, if you add that variable with 1, the output will be always 1. Because if x is equal to 0, if you substitute here x equal to 0, you will get 0 plus 1 is 1. If you substitute 1 here, then 1 plus 1 is also 1. So that is dominant law. 1 is dominant here. And if you add any variable with 1, the output will be 1. Similarly, if you multiply any variable with 0, you will get 0. Irrespective of the value of the variable, you will be getting 0. And the next law is involution law. If you take double complement, which means first you take complement, then you take another complement, then you will get same variable, which is like a bar bar. Okay, so you have variable a, then you take a bar, so that will be the complement of a. Okay, then you take a double bar. First you take a bar. So if you consider a equal to 0, then a bar will be 1, complement of that. Then you take complement of that again, then you will get 0. So a will be equal to a double complement, or a double complement will be equal to a, whatever the value it is. If you take 1, then the complement will be 0, then double complement will be again 1. So a double complement will be equal to a itself. Okay. Similarly, if you take dot product or plus, dot or plus, you take double complement of this dot, then also you'll get dot. The operator will be same. Okay. So that is the involution law. Now you have a commutative law. This is just interchange. Don't worry much about these terminologies, commutative, associative, all those things. That is not that much. Just consider x plus y, which means you are adding two variables. Then change its order. Change it as y plus x. Both will be same. If you add a plus b, that will be equal to b plus a. If you add c plus d, that will be equal to d plus c. Okay, so the order is not important. Only that operation is important. So a plus b will be equal to b plus a, or x plus y will be equal to y plus x. That is the commutative. Similarly, for product also, x dot y will be equal to y dot x. A dot b will be equal to b dot x. Okay? A dot b will be equal to b dot a, or c dot d will be equal to d dot c. That order is not important. Only that product, you can change that order. Okay? And the associative law. In the case of associative law, you can see from here x plus y plus z, x plus y plus z. In this case, you have given bracket to y and z. right? Y or Z, that is y plus Z. You have given bracket to y plus Z. At the same time, you can also write this expression as x plus y plus Z. Okay, so first you are adding y plus, in the first case, you are adding y and Z. Okay, then adding that result with x. That will be equal to adding x and y first, then add that result with Z. That is the associative law. Similarly, for the case of product, if you are taking product of y and z first, then taking product that the result of y and z with the x, that will be equal to taking product of x and y first, then taking product of that result with z. So this will be equal. This is called associative law. You can associate any variables irrespective of the order. Okay, that association is not a matter. You can associate, first you can associate y with z. At the same time, you can also associate x with y. That both will give you the same result. Now the next one is distributive law. Distributive law. In the case of distributive law, x dot y plus. This is just taking the expansion of the bracket. Okay, x dot y plus z. Okay, so first operation is y plus z here, but you can expand this bracket in such a way that x dot y plus x dot z, x dot y plus x dot z, because x is multiplied with both y and z. And here also on the other side you can see here x plus y dot z, you can write x plus y, okay, x plus y dot x plus z, x plus z. So in this case you can also put a bracket here. Okay? X plus y dot z will come. Okay, so this will become x plus y. Sorry, this bracket should be with dot product. Just put a bracket with a dot. Okay, so in this case x plus y dot x plus z. So in that case, you just expand that bracket with the operator which is outside the bracket. And then De Morgan's theorem or De Morgan's law, you can see x plus y whole bar. This we already discussed. X plus y whole bar. Okay, we have put a bracket here, which means this dash or bar which is applicable to both everything which is inside within this bracket. Okay, everything which is inside this. So x plus y whole bar, which will be equal to x bar dot y bar. Similarly, x dot y whole bar, x dot y whole bar, which will be equal to x bar plus y bar. This we already discussed. This De Morgan's. Then we have this absorption theorem. This is very important. Absorption law. This is very important. X plus x dot y. X plus x dot y. This will be equal to x. This is very important. And similarly, x dot x plus y also equal to x. Remember that x dot x plus y, this is equal to x. So you are just taking product of one variable with the same variable which is added with another variable. Okay, this kind of situation. If you have any, it's like if you have a dot a plus b, okay, this is also a. This will give you a. So you are taking the OR operation with the variable a and b. Okay, then taking product of that result with a, then that will be a itself. This is very important. Okay, this absorption theorem is very important. Similarly, a plus a dot b, this also will give you a. And one more thing I have to mention here, similar to this one, this absorption theorem, you can apply it for both. we have one more absorption theorem, which is A plus, sorry, A, you can also give that plus A dot A bar plus B. A dot A bar plus B, which means the variable which you are taking the product is A, and inside the bracket you have the same complement of the same variable. Inside the bracket you have the complement of the same variable which is added with B. Okay, so inside the bracket you have complement, outside the bracket you have the variable in the original form. In this scenario, the output will be A plus B. This scenario, the output will be A plus B. This is very important. These two are very important. I have to keep that in mind. A dot A plus B will be equal to A. A dot A bar plus B will be equal to A plus B. You can also substitute some, or you can expand that and find out how it is working or not. That you can do. You can just expand this if you need. Then you can find out whether it is working or not. Okay, so now these are the important theorems or laws. Keep this in mind. De Morgan's theorem and absorption theorem are very important. Okay? De Morgan's theorem and absorption. Absorption theorem means these two are very important. Both the absorption theorem are very important. Okay, this absorption theorem and De Morgan's theorem are very important. Absorption theorem is very crucial. Okay, so okay, let's do this example. Okay, just consider this Boolean expression, and this Boolean expression reduces to. That is the problem. The Boolean expression y equal to A bar B bar C bar D plus A bar B bar C D plus A bar B C bar D plus A bar B C D reduces to. Just try to do this.
Option D, sir.
Option
D.
okay, option D. Anyone else? Just to use these theorems that we have here and solve this. We will also solve that by using some other techniques later.
Option D, sir.
Okay, let me do that. So you have the expression A bar B bar C bar D okay, A bar B bar C bar D plus A bar B bar C D plus A bar B C bar D plus A bar B C D. Now, first thing you have to do is you are simplifying this. So all the terms are having four terms. Okay, each of these terms are containing four variables. Okay, then you can consider taking the common terms outside. So in the first two term, you can have A bar B bar, which is common. You can take that outside. Then C bar D, C bar D plus. I'm just doing that in the conventional way. Okay, the simplest possible way. So C bar D plus CD, and the second term you have A bar B is common. So A bar B into C bar D plus CD. Then here you have A bar, B bar, C bar. Inside this C bar D plus CD, what is common? The common term is D. So D into C bar plus C plus A bar B into the common term is D here. Then C plus C bar. So what is C bar plus C? Any complement, any variable which is added with its complement which is equal to 1. Okay, C bar plus C is 1. Any variable which is added with the complement is 1. So this is also 1. So then you will get A bar, this is A bar B bar D plus A bar B D. Okay, and from this you can take A bar D as common. This implies A bar D is common. Then you'll get B bar plus B. Again, by theorem, if you add a variable with its complement that is equal to 1, then this will give you A bar D. Then your option D is the correct. So I have just written all these steps so that you can understand that. So this is how you can do this problem, this kind of problem, and you can use all these theorems for that. Now we will move to the next section, which is the K-map, and after that we'll do some more problems with this. Okay. I hope we have time for that. Okay, so we'll be discussing K-map now. So in this section, what you have done in this Boolean expression, basically what you have done is you have a long expression. Here you have a long expression y equal to A bar B bar C bar D plus A bar B C D plus etc. etc. So this big expression, you have reduced that expression into a simple form, that is A bar. Okay, which means that in this expression, if you are considering this expression itself, you are using this as an AND gate. Okay, A bar dot B bar dot C bar dot D. For that you need an AND gate. This term need an AND gate. This term need an AND gate. This term also need an AND gate. So you have to use 4 AND gates here. All these are product terms. All these are product terms. This is product term. This is product term. This is product term. This is product term. All are multiplied. Okay. So all these are product term, and they are added. You can see addition here, plus, plus, plus. So these product terms are added here, and this kind of expression we call it as sum of products, which is another way, which is SOP. You can call it as, in another way, you can call it as SOP. SOP means sum of products. Sum of products. What you are doing, you are adding different product terms. Okay, then it is called a sum of products. SOP. So this is one way of writing the expression. At the same time, you can also write the expression like A plus B plus C plus D. Then dot sum A bar plus B bar plus C bar dot A bar plus B plus C, something like this. So in this case, these terms are sum. These terms are sum. Okay, they are just added. So these terms are sum. They have in between them, we have these dots. These dots. So this kind of expression we call it as product of sum, POS form. So you have expression, Boolean expression in 2 forms. One is sum of product form, where you will be adding different product terms. Then you have product of sum term, which means you are taking product of different sum terms. Okay, so each of these terms are sum terms. and you are taking product of. Okay. One more thing you have to remember is in SOP, that is sum of product form, which you are adding different product terms. Each term represent one. Each term represent one unit. Each term represent one. Or this is called min terms. All these are called min terms. Min terms means which are representing one. Are representing. At the same time, when you consider pose or product of some form, if your Boolean expression y equal to in product of some form, each of these term represent zero. Each of these term represents zero. This is called max term. This is called max term. Just to keep that in mind, we are not going to much deep theories. Just to keep that in mind, when you consider SOP, that is sum of product form, each term is called min term, which represent one. And in case of product of some form, if your Boolean expression is in product of some form, then each term is called max term, and they represent value 0. Okay? Just to understand this concept, then we can easily understand the CAM. Okay. So what you have done here is you have reduced this much of big expression into a simple form. In this expression, as we discussed, this is a product term, this is another product term, this is another product term, this is another product term. So 4 product terms are there, which means you need 4 AND gates here. 4 AND gates here, and then all these output can be given to an OR gate. So you need 4 AND gates and 1 OR gate, and along with that you need NOT gate also. You can see NOT gate here. Complement, for taking complement you need the NOT gate. So you need more gates, and more complicated circuit will be corresponding to this expression. Okay, but when you reduce that by using the expression by the theorems, Boolean theorems, different theorems or laws, then you can reduce that into a simplified form. As you can see here, this is A bar D, just A bar D. So this is the simplified form. So by using that theorems, Boolean algebra, or that theorems and laws, you can reduce that big expression into a small expression where you will be needing only one AND gate. Okay, you just need one AND gate because A bar D, only one product is there, and you need one NOT gate. Okay, so your number of gates will be reduced, and all the number of gates will be reduced with the circuit. Digital circuit will be much more easy, okay, to construct. Okay, much more easy to construct. So for that we have to do this kind of a Boolean reduction of Boolean expression by using Boolean algebra. But some more, this is also difficult, because when you are having some complicated expression, then it is difficult to simplify them by this kind of methods. Then you have a simplified method to uh, simplify the Boolean expression much more easily is the CAMAP, which is called CAMAP simplification, or CAMAP, which is used to simplify the Boolean expression in much more easiest. Okay, this is K-map, or you can call it as Carnot map. Okay, Carnot map, which is saying. So this Carnot map is also, this is just a pictorial representation of the truth table, and this is used to reduce the Boolean expression, especially when the Boolean expression is very long or complicated. You can use this K-map to reduce them. You can also use the theorems or laws that we have discussed earlier to simplify that uh, by using that expressions. You can simplify this long expression, but that step or that method is much more complicated, because you should know all the theorems. You should apply all those theorems in that steps, in between the steps. Sometimes the steps can get wrong also. So this is much more easy. CAMAP is much more easy. Only thing that we have to consider here is how you can simplify these steps to simplify using CAMAP that you have to consider, you have to study, and what are the important things related to CAMAP. So that we will be discussing here, and we will do some problems. So here you can see the CAMAP simplification. First thing that you have to understand that this is the pictorial representation of truth table, and it is used to simplify the Boolean expressions. And if you are having a CAMAP will always related with the size or number of cells, and size of the CAMAP or number of cells in CAMAP, which is nothing but 2 raised to n. I don't know whether you will be able to see this. This is 2 raised to n. 2 raised to n, where n is the number of input variables, a, b, c, d, etc. How many number of inputs are there? That is represented by n. And 2 raised to n will be the number of cells or the size of the CAMAP. Okay. So, for example, we have given here, if you are having 4 inputs, I will zoom it a little bit so that you can see. If you are having 4 inputs, then your size of the CAMAP or the number of cells will be 16. That is 2 raised to 4. 2 raised to 4 will give you 16 cells. Okay, so the size of the CAMAP is 16 cells. The first step is to find what is the size of your CAMAP. So if you have given 4 variables, 4 inputs, then the size will be 16, which means you need 16 cells of CAMAP with 16 cells to solve that particular problem. Now, these are the representation of the CAMAP. You have n equal to 2 here, you can see, which means 4 cells are there. 2 raised to n is 2 raised to 2, that is 4. And then when n equal to 3, which is number of variables or number of inputs equal to 3, the number of cells will become 8. The 8 cells, you can arrange it horizontally or vertically. Both are possible or both are same. And then when n equal to 4, which means your input number of inputs are 4, then you need 16 cells for your CAMAP to solve the problem. Okay. I hope you understood the size, how you can calculate the size of the CAMAP. And then we are going to the representation of address in the CAMAP for each cells. As we discussed, we have 2 different way of expression, Boolean expression. One is sum of product form. Okay, one is sum of product form. The other one is product of sum. Sum of product means you will be having different product terms. You are adding each of these product terms. Most of the time, this kind of forms will be asked. Sometimes they can ask pose, but it is very rare case. Product of sum, in the case of product of sum case, we will be having different sum terms that will be product. You have taken product between them, okay, or dot, and you have taken the product of each term. So as we discussed earlier, in the case of sum of product term, very important, A will be taken as 1, A bar will be taken as 0. Remember that in SOP form, A will be taken as 1, A bar will be taken as 0. Which means if the variable is as such, it will be taken as 1. If the variable is in complement form, it will be taken as 0. You will understand that little after some time. Okay, so A will be taken as 1, A bar will be taken as 0 for the case of sum of product form. But in the case of product of sum form, just opposite. Product of sum form, A will be taken as 0 and A bar will be taken as 1. A bar will be taken as 1. So we are not going to discuss all the theory, just to remember all these things. In the case of sum of product form, A will be equal to 1, which means if the variable is in its real form, it is 1. If it is in the complement form, it is 0. Okay, you just have to study only this. Okay, and just opposite of this will be the case with the product of sum form. Now, as we discussed in the case of sum of product form, you have to fill with min terms 1. And for the case of product of sum form, you have to fill with max terms or zeros. And in normal cases, the problem, sometimes they will ask problem like this. F of A, B, C, D is this. You can see from in this, this is one kind of expression. I will just discuss this. You can see this K-map representation here for sum of product form. This is a four variable K-map. I'm talking about this one. Okay, this one. 4 variable K-map. I will just explain that. So you can see in this K-map, you can see, I will just explain that here. We'll just draw that so that you can understand. So let us consider a 4 variable K-map. 4 variable means you are having 4 inputs. Okay, when you are having 4 inputs, the number of cells will be equal to 2 raised to 4, that is 60. Okay, that is the size of your K-map. So just to draw 16 cells. Just to draw 16 cells. 16 cells you can draw easily like this. 1, 2, 3. This is not equally distributed. Anyway, okay. So this is the 4 variable K-map. Now the problem is where you will fit your inputs. So for that we have to use this corner. Then first you can write A. For example, you have 4 variables. Let us take this as A, B, C, D are the inputs or the variables, 4 variables. Then you can take A, B this side and C, D on this side. You can also consider A, B on the other side also, C, D on below. That does not make any difference. Yeah. Now remember, the cell that you are representing here, what are the terms which will be coming inside this cell? We'll just zoom it a little more that you can see. Consider this cell. First cell you consider first cell. Okay. So first you have to consider the first cell. This will be first I will write this address. Okay. This is C bar D bar, C bar D bar, and this is A bar B bar. This is A bar B. This is C bar D bar, then C bar D. C bar D. How I am writing this? You have to write it like 0, 0. This is also 0, 0. Then you will get 0, 0, 0, 0 here. 4 zeros. 2 from this side, A bar, B bar. Then 2 from this side, C bar, D bar. Okay, 0, 0, 0, 0. Which means first one is A bar, then B bar, then C bar, and D bar. Next one is C bar D. What is that? C bar means 0. That is what I told you in the case of min terms, or when you consider product of some term, sum of product term, you have to consider the variable as 1 and variable complement as 0. So C bar you have to consider as 0. D you have to consider as 1 because it is in original form. D is in original form. So what is the value in this cell? It is 0, 0. That is from A bar, B bar in the row. Okay? A bar, B bar is 0, 0. Then 0, 1. So this is 0, 1. So 0, 0, 0, 0 represents 0. Decimal equivalent of 0, 0, 0, 0. 0, 0, 0, 1 represent 1. So this is 1. I hope you understood this decimal equivalent value 0, 0, 0, 1, which means when you convert that into decimal, what you have to do? Decimal value 1 into 2 raised to 0, last digit. 1 into 2 raised to 0 plus 0 into 2 raised to 1 plus 0 into 2 raised to 2 plus 0 into 2 raised to 3. So all these things are 0, only this remains. So 1 into 2 raised to 0. 2 raised to 0 is 1. So 1 into 1 is 1. So this result in 1. So decimal equivalent of this expression, that is 1. Then this cell will be having address 1. Okay. I hope you understood this. And the next one is CD. Next one is CD, then CD bar. Okay. Why I am writing C bar D, then CD, CD bar? Because when you jump from one column to the next column, or one row to the next row, or in simply means from one cell to the next cell, only one variable should change. Only one variable should change. First, you consider C bar, D bar. In this case, C bar, D bar. When you jump to the next cell, this D bar becomes D. C bar becomes C bar itself. Okay. So there is no change in C bar, but D bar changed to D. So only one variable is changing. Then when you consider C bar D into the next cell, okay, when you consider next cell, C bar D is changed into CD. D remains as such. C bar becomes C. So only one variable is changed. But if you put C D bar here, suppose C D bar is here, then D will be changing to D bar. C bar is changing to C. That is not possible. So two variable change is not possible when you consider the adjacent cells. So considering the adjacent cells, only one variable should change. Because of that, after C bar D, CD will come. Then CD bar. Okay, C is same, D is changing to D. Similarly, going down, you have A bar B, no problem. B is change, B bar changed to B. A bar remains as such. And A bar B in the next row or next cell, you will be having AB. Instead of A B bar, you will be having AB because A bar changed to A, B remains as such. So only one variable is changed. Then AB, then AB bar. Here A is remaining as such, B is changing to B bar. Okay. Now just to write what is this side and what is on the cell side. So here again A bar B bar, that means 0 0, and above you have CD. CD means what? 1 1, because it is not in the complement form. Then you just put 1 1. So 1 1 here. Then again 0 0 from A bar B bar. CD bar. C is 1, D bar is 0 because it is in the complement form. Complement form, whatever it is in complement form, that is in 0. Whatever it is in real form, that is in 1. So 0 0 1 1, what is the value? 3. Okay, 1 plus 2. Then 0 0 1 0, this is 2. Next case, you can complete these cells. Next one is A bar B. A bar B means A bar is 0, B is 1, C bar D bar 0 0. Then A bar B, C bar D. Then you can write A bar B, C bar D means A bar means 0, B is 1, C bar is 0, D is 1. Okay. In the same way, you can complete this. What is 0 1 0 0? I will just write here 0 1 0 0. Multiply that 0 last digit. 0 into 2 raised to 0 plus 0 into 2 raised to 1 plus 1 into 2 raised to 2 plus last one 0. 0 into 2 raised to 3. 0 1 2. So this will give you plus this one is 0. 0 multiplied with the 2 0. 1 multiplied with the 2 square 4. This is 0. So finally you'll get 4. So this one is 4. This one you'll get 5. This is 6. Then this is 7. When you do this binary, then you can understand that. This one, what is this value? AB. AB is 1 1. C bar D bar 0 0. And when you
12, sir.
calculate, sorry,
12, sir. 12, sir.
12. Okay. So this one will be 12 when you convert that into decimal. then this one will be 13, and this one is 14, this one will be 50, and this is 8, 7, 8. After 7, this will come 8 here, then 9, 10, 11. So just look at this address. These are called address of the cell. 0, 1, 2, 3, etc. All these things are address of the cell. And remember that this is 0, then 1, 2 will come at the end, then 3. Okay. 4, 5, 6 come at the end, and 7. Then 8 will not come here. 8 will come below, because in this direction also we have that same rule. Okay. So in this direction you can see after 7, 8 will come here, 9, 10, 11, 12, 13, 14, 15. Okay. So first you have to remember this thing. Okay. Otherwise the entire calculation will become wrong. 0, 1, 2, 3, 4, 5, 6, 7. Okay. Then 8 comes down, 9, 10, 11, 12, 13, 14, 15. So both row wise and column wise we have this jump. Okay, so these numbers are representing the address of each cell in the K-map. So in the question, either they can give the expression or they can give this cell address, which means if you have given y equal to a bar, b bar, c bar, d bar plus y equal to a bar, b bar, c bar, d bar plus some other value a bar, b, c bar, d bar. Let's say this is the expression. So this one represents the first cell, okay, with address 0, and this, so this address is 0, right. Address is 0, and the a bar, b, c bar, d bar, which is this cell, with this is having address 4. Okay, so the expression, when they give expression, it will be like this in the sum of product form. When they have given only this address, then that form will be in this format, as you can see from the here. If they have given address, then that will be in this form. What it gives you, it says this is the function f with the variable a, b, c, d, which means 4 variables are there, and this sigma, I hope you can see this expression. This sigma represent, this sigma you can see here, this sigma represent the sum of product form, this sigma, and this small m represent min terms. Okay, when it is sum of product, it is min terms, and all those min terms are in these addresses. So addresses are given, cell addresses are given, expression is not given. So in each cell we have that expression. Okay, and in the same way you can see here also on the other side you have for the product of some case, same function f, a, b, c, d are the variables. So there are 4 variables. If you are having pi here instead of sigma, that is capital pi, then it represents force form, product of some form, and capital M, that represent max terms. So if it is pi and capital M, which is representing product of sum with max terms, and they have given address. And in the first case, you can also see something d of 2, 7, 8, 10, 13, etc. What that means? D of something. That means these are don't care. D means don't care condition. D means don't care condition. It is very simple. Don't cares are very simple. It can be either 0 or 1, so that if you need a very big grouping, a big group, you can add with the group. If you don't want them, you can just neglect them. Okay, we will do the problem, then you will understand that more clearly. Don't care, whatever which is coming as don't care, which means 2, 7, 8, 10, 13. In these cells, which is don't care we usually represent with a cross, as you can see here. You can attach those cells with your group if you need. Otherwise, you can just ignore them. Okay, that is the don't care condition. So if you need a very large group, then you can take them. If you don't need them, you can just neglect them. Okay, that is the condition with the this don't care. Now, how you fill this? If you have given expression like this, as we discussed, this is SOP form, sum of product form, and you have min terms sigma small m. Then you just fill with this address. You fill 1. Okay, for 0 you fill 1. You can see here. Address 0 you fill 1. For address 4 you fill 1. Where is 4? 4 is 1 here. Then for 5, address 5, cell address 5, cell address 5 is 1. Cell address 14, where is cell address 14? Cell address 14 is here, is 1. Then cell address 15, it is 1. So this much of cells are given in the problem where you put 1 because you have min terms, sum of product form. But at the same time, you have don't care also. So in these addresses, you put don't care. 2, 7, 7 you have cross. Then 8 you have cross. Okay, so all those don't care addresses, wherever it is given D of that address, that you give cross, which means these cells are don't care condition, having don't care condition. You can either take them as 0 or 1. Okay, on the other side, if you have given product of some form like this expression, like capital pi and capital M, which means they are representing product of sum and max terms. When it is max terms, you have to fill with 0. These addresses you have to fill with 0. So in this case, you have address 0 to 6. So in 0, you have to fill 0. Then 2. In 2, you have to fill 0. Then in 6, you have to fill 0. Where is 6? Here. Then 7, you have to fill 0. 8, I think 8 is below. So in all those addresses given in the problem, you just fill zeros and then group these zeros. Okay. Now we have discussed in sum of product form how you fill the min terms, that is 1, and in the product of sum form how you fill zeros or the max term. Now we will be discussing the grouping in CAMAP. Okay, don't confuse these things. When you do the problems, you will understand each and every steps very clear. Okay, so these are the steps involved in grouping. These are the steps involved in grouping. These steps must be followed when you simplify the expression. Okay, so far if you have any doubt, you can ask. If you have any doubt, you can ask. The expressions in the explanation. Otherwise, we just to go to the next step. Okay, we'll do one problem in this section today, and we'll continue the problem section tomorrow in the next class. Okay, these are the important steps. So we'll just quickly go through the steps for grouping. How you group these midterms and max terms. Okay, after grouping only you will get the simplified expression. So the grouping, you can see from here, first point, the adjacent cell has to be grouped. Okay, with whether it is max term or min terms, does not matter. If it is 1 or 0, whether it is 1 or whether it is 0, it is not a matter, but only the adjacent cells you can group. That is the first point. You cannot group random cells, only the adjacent cells. Okay, which means if you are having some cells like this, for example, I'm just drawing this. Okay, I will just draw this. Okay, let us consider 16 cells here itself. 16 cells. Okay. So adjacent cells you can group. Only the adjacent cells you can group. These two cells, yes, you can group. These two cells, yes, you can group. Okay, these are adjacent cells. You cannot group this one with this one. Okay, this grouping is not possible. I hope you understood. Only the adjacent cells can be grouped together. That is the first point. And the second point, group should contain number of cell in powers of 2. Okay, only these kind of groups are possible, which means these are in powers of 2, like 2 raised to n form. N can be 0, 1, 2, 3, etc. So in groups, when you are grouping, it has to be in powers of, the number of cells in that group will be equal to powers of 2. It can be 16 cells, it can be 8 cells, it can be 4 cells, it can be 2 cells, it can be 1 cell, single cell itself. But it should not be 15, it should not be 9, it should not be 7, something like that. It should follow this order, 2 raised to n form. Okay, that is the second thing. So your cell, the group should contains either 1, 2, 4, 8, 16, then 32, etc. in this form. So the order should be 2 raised to n, 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3, etc. That number of cells will be in the group. Then the third grouping, third point is grouping should start from the maximum size and end in minimum size. Okay, first grouping should have the maximum number of cells. The last group should have the minimum number of cells. Okay, that is the third point. First grouping should be the large one, or the number of cells should be larger for that one, and the last group should have the minimum number of cells or the minimum size. And the fourth one is number of groups should be as minimum as possible. Okay, number of groups should be as minimum as possible. Then only the expression that you are getting after simplification will be the simplified expression. A simplified expression. Okay? So the number of groups should be as minimum as possible. As minimum. If you are having a large number of cells, and if you are making only one cell, one group out of it, that is the best. Okay, the number of groups should be minimum as possible. Okay, and then the fifth one, the don't care cells can be grouped with 1 or 0 to increase the size of the group. Otherwise they can be excluded from the group, which means if the don't care is coming very near to a cell, and you can add them into a group so that the group will become larger, or size will increase, then you can take that don't care cell. If there is no use of don't care, then you don't have to use that. Okay, when we do the problem, you will understand much more clear. And the last one, all the edges of the K-map are connected to opposite edge. Okay, so when you consider K-map, the opposite edges are connected. So I am just drawing a simple diagram here, just to show what that means. This side of the K-map is connected to this side, like you are folding a paper. If you are folding a paper in such a way that the edges are touching. Okay, so these two sides are touching each other. Similarly, these two sides are touching each other. These two sides are touching each other. So if you are having a one here, a cell here, if you are having another one here, these two can be grouped. These two can be grouped because they are touching each other. So the edges of the K-map are touching to the opposite edge. Okay, that is the sixth term. So you have to follow these 6 points when you do the problems. Then you can easily solve any problem. So let us consider this problem. Then we will stop. We'll do the other problems in the next class. Just erase this. Okay, consider this problem. We can see here a 4-variable K-map a 4-variable switch